Perfect. Great. I'm going to close the door now, I think. So the way we typically do this class is I'll do probably 40 minutes, 50 minutes worth of talking through some slides now, and then we'll have some exercises. You have time then to do some exercises. I'll be in class to help. Once we've done those, we will then launch into the second session. So we're going to try that style today. On Friday, we're going to do it differently. We're going to try course. So we're going to do a longer session. And then on Monday next week, you guys can vote and decide how you want to do this. Do we want to have a session, then a break and another session, or do we want 2 sessions side by side? Again, if you're going to miss class, just let me know. It's not a problem. Okay, so this is what we're going to discuss in our first session today. We're going to briefly talk about the setup. We will need to use the breaks if you're having trouble setting up R in RStudio. You don't want to necessarily stop the class, but in the break, I can come around and help set up. I'm then going to give you a little bit of a background to R, why it's so exciting, why it's so cool to learn. And then we're going to jump into data types, how we actually handle our data in R. And then we're going to get reading and writing, because we need to get data into R, and then we want to write it back out once we have our results. So this course is very practical. We're going to teach you just what you need to know really to do next generation and bioinformatics, next generation data sequencing analysis. So we're not going to cover everything, but if you have any gaps or if you want to ask questions, please reach out and we'll try and address this for this class. So as I said, all our prerequisites should be on this page. If you click there, it's going to take us to our R page, or it's going to be available here. You can download, get the zip, and start following along on your computer. Once you have that downloaded, you should be able to go to the R course in there, and you'll find all the presentations in separate folders, all the exercises and all the answers. But hopefully I showed you, in reality, you just need to click on this index, and it's going to take you to the same page we're looking at public. I'm going to show you how to do this in our first session, but just every one of these classes is going to remind you to do this, and that is to set your working directory. And we can do that in RStudio. I'll show you that in a few slides. But really setting your working directory just tells R where to look for files. So you set your working directory to where all your files you want to process are. And that's why we're setting this here to this zip file you just downloaded, and I'm setting it to R. Again, we're going to show you how to do this in a few slides. This is the beginning of every section, every course. We're going to show you how to set the working directory. So first off, what is R? Who has experience with R in this room? I know you do, Sarah. I know you do. A few people. Who has experience with programming languages? So you didn't have experience with R, though, right? So Python or Python? So yeah, Python is I would say is a programming language, and I'm going to refer to R as a scripting language. Really, it's just to do with the speed and capabilities of R versus Python. Python tends to be a little bit faster. But what R has is incredible support for the bioinformatics community. It is a scripting language, and really it's built for originally statistical computing. And it's built by these two gentlemen, Robert Gentleman, who we had at Rockefeller a few years ago. He came and gave a talk when we hosted the Bioconductor conference. Super clever guy. And Ross Harker, who isn't so involved with R anymore. And there's obviously another R who I don't mention here, but Brian Ripley, who is behind most of the packages we will use now. So R comes from something called S. It's just a play on S that these two guys called it R with their names. That was developed in Bell Labs. And S is great. It's great for statistical analysis. The problem is it's not open source. It wasn't particularly cross-platform, but it was suited for very high-level data analysis. So this is once you've summarized your data, You can then use R to make really quick plots, very intuitive plots, to do further statistical analysis. But maybe R wasn't originally written to trawl through gigabyte large files. It just wasn't written. It really does have extensive graphics capabilities. I think R is one of the best languages for doing graphics. I know Python has some great tools, but I think it's actually taking a lot of inspiration from R. It has an incredible diverse range of add-on packages. So this is really useful that we don't need to write everything we need to do in R. Other people have written functions, tools, protocols for us, and they put these into what we can call packages. And we'll see a bit of that in a few slides. There is an incredibly active community of developers. I think R is one of the communities we're in, but there are thousands of people building packages, and they're very responsive. So you can go on and ask questions and get support in R pretty, depending on where you go. I'll show you a bit of that later. Various levels of friendliness. R help very unfriendly. Have something like Stack Overflow a little bit more friendly. You know, concise, they would call it, rather than less friendly. And something which is really fantastic about R, and we're going to use this so much, is it has incredibly thorough documentation. And that's because when they established R, they made it part of the protocol in making these packages that you have to have documentation. You won't be able to get into their systems where they host all these packages unless you followed those rules. So one of the reasons why I think a lot of people come to R is that you're actually going to get straight out of the box incredible graphical capabilities. You can make some really nice plots, not necessarily this plot. But things like ggplot as well with extended packages, you can do some really nice graphics. There are access now, and I wrote this a few years ago, this particular slide, but I think there's like 20,000 packages available in CRAN, which itself is based on the Perl libraries. We have, let me try that. So CRAN here, comprehensive R network. If you have a look, you can see they've got, I think it was 20,000 packages, but just tons of packages doing all sorts of different, very tailored, very specific functions, and we can borrow and install these packages to make use of the functions within them. You also have, I think I pointed there to MRAN. I got some sad news about MRAN. Yeah, actually, if you go to home on MRAN, or maybe it's not saying it here, but it's going to close on July the 1st this year. So it's going to close next week or this week. That's sad. I need to update my slide. So, you know, Microsoft invested heavily in R, and they bought Revolution Analytics. The reason they're closing this down isn't because they've stopped supporting R. It's because POSIT and the people who write R Studio have really taken over this particular one. Okay. Somewhere we're going to use extensively is Bioconductor. So this is R packages really written for bioinformatics, mostly microarrays originally, then next generation sequencing, but proteomics, image analysis, all this is then contained within Bioconductor. And we'll come to them later, but the fantastic thing about Bioconductor is they've taken this idea of needing support, needing documentation to the next level. Bioconductor packages really are great documentation, a vignette to talk you through the entire analysis. And it was really Robert Gentleman, who was one of these people in R. One of his big things when he stepped out of the main R kind of core group was to establish this by there. Hundreds, thousands of packages now available to work on computational biology, but in particular, high throughput sequencing. So to get R, we need to do, or to get set up for this class, we're going to do two things. We're going to first install R. And again, we're not going to do this in class. Feel free to give it a go, but I will help you in our break. So we're going to install R, and then we're going to install something called an ID. Right, so this is a integrated development environment. It's effectively a nice GUI for R to sit in that allows us to kind of interact with it without having to use the terminal. So I say here, RStudio and R is installed on your machines, possibly. Who's got R and RStudio installed right now? Oh, I got old. Great. I will help you set it up, set it up in the break. But we're just going to take us there now. Well, our project website I already have open. It's the same as this CRAN website. So here is our home. And I think if we wanted to install it, we could go to the R binaries, find our particular program or version for our operating system we're using, computer we're using. Usually it's pretty clever and it knows what you're on when you actually come to the page. Here it doesn't. So I'd have to click download R for Mac OS. There's a lot of Macs in this room. There's a ton of Macs in this room. But you've got Windows as well, and then Linux. Linux can be a bit of a pain. You need to install from source. And then if we go to the RStudio website, which is now POSIT, you can see they got a big button here, download RStudio. If you click that there, it's going to take me to another button, download RStudio. And then eventually it's going to tell me the two things I just said. We need to install R, follow that, follow the instructions, install R. And then we'll install RStudio, which is again just a wrapper, nice little home for us to interact with R. Okay. Ask, who here's got a Linux computer? Is anyone working on Linux? Oh, good. That's going to save me a lot of hassle. Great. Let me just double check I'm recording. That doesn't look particularly. Oh no, I am recording. Here we go. Okay. So, quick look at RStudio. Before I jump in, and I'll show you it in the class now, but we have a files and directories kind of section. When we open RStudio, we have an environment and history. We're going to have the actual console. So this is where R sits. So R is in this part of this program. And it's up here that we have kind of a text area where we write our code and get ready to put this in the console. So I usually have RStudio open somewhere on my computer. Here we go. So let me start a new file and then something at the top. My computer's going to be a little slow. It doesn't like Zoom. So here we have this R terminal on the bottom. So you can see it's loaded up. I'm on R 4.1.2. Here we have just a place we can write how we want. And if we want, we can save our scripts from here as well. Save as. Save these to my computer. Gosh, my computer is slow today. It's going to save that hopefully with an R extension. It knows it's an R file. Here I have my environment. So when I start to build and make objects, they're going to appear here. We'll see that as we go along. I have very usefully a history. So anytime I've done something, I can see it appear in this window up here, which is useful if you've forgotten what you did. You can also search your history. It's not particularly useful because I just have one thing in my history. Oh, it's pulled up my old history as well. And if I want to, and I've found something in my history I'm particularly excited about, for instance, I can send that to my script. And it's going to appear over there. Or if I want to, I can select lines here, and I can tell it to run this line. And it's going to run it inside the R console. So then it's taken what I put up there, and it's evaluated it. Okay, I think another way to do that is I can just press Command Enter next to the lines I want to run. And it will run. I realize that some of you will know more RStudio tricks than I do. Feel free to jump in if you have any shortcuts or anything. Okay, so that's RStudio. This is really where we're going to write our scripts. And here we're going to evaluate things. So we'll jump into what types of data do we have? We'll start very simple. We'll just deal with some simple calculations, variables, and then we'll look at vectors, which are just one-dimensional arrays of numbers or characters or logics. We'll then look at matrices, so how we hold 2D data, tables in R. And then we'll get into more complex data types like data frames, which done Python, you'll know pandas. But data frames are really a more complex version of a 2D table, right, where we can have column-specific information. And then finally, I think the last thing we'll look at is lists. And lists are our way of really handling any data type. We can usually force them into a list. So let's start simple. So I'm going to really stay on the slides most of the time. Let me know if you want me to show you something in R. I'm really just going to hop into R and R Studio when I need to show you some operation within them. So in its most basic, R is just a simple calculator. Okay. If I want to, as I just showed you, I think I just did 4 plus 6, but we can just type in numbers to our R Studio, our R console, and it will evaluate them for us. So 3 plus 1 is 4, 2 times 2 is 4. And then we can also do things like you might do with a graphical calculator. We can do, say, the square root of 25, and then subtract. Having just said that, I will hop into R Studio. So what did I do? 1 plus 3, 2 times 2. And then square root 25. Square root 25. Yeah. So already we've seen, I think, here our first use of a function, very simple function. But this square root 25 demonstrates something simple use of a function. And functions in R are effectively just tools to allow us to perform a complex operation on its arguments and then get the result. So in R, arguments provided to our function within these parentheses, these types of brackets, and they follow the function name. So in this case, we had square root, right? Square root's the function name, and then we have brackets, these parentheses. And then within those parentheses, we have the argument that we're passing to that function. So we're passing 25 as an argument to the function square root, and then it's going to return to us the result. I don't evaluate that here, but we just saw in R Studio, square root 25 gives. So that is how all functions work. We have the name, have the parentheses, and we have the actual argument we're passing to there. We'll evaluate it and pass the result back. Some other really simple functions to know, easy to pick up: min, sum, max. So these take arguments in any order. We just need to separate the arguments by a comma, and in functions, always your arguments are separated by comma. So here I'm going to pass in 3 arguments to the min function. I'm going to pass 2, 4, and 6. And it's going to evaluate and find me the minimum of all the arguments passed to it. Okay, so that gives me 2. With sum, I'm going to get very simple. I can just pass in the arguments in any order: 2, 4, 6, 12. That's the sum, right? Yeah. And then max, 2, 4, 6. That's the max of that, and it's going to give me back 6. The important thing is here we have a function name, a parentheses, and then the arguments go in the parentheses. If we have more than one argument, we have to separate our arguments by comma, and then they will evaluate them. So R has many useful built-in functions. So square root is built in for us, mean, max, these all come as soon as you've installed R, they're available to you. If we want to see how any of these functions work, we just need to either Google it, that's probably where I'd start, but you also have a help built into R, which is really useful. And actually, to be fair, you'll go here first before you Google. Right? So let's try just doing this for the square root. Okay. So when you're working in RStudio, you do something like question mark, and then the name of the function, right? So I've done this, but I could choose any of the functions we've seen so far. So I do question mark min. Okay, it's going to go look and find the description of how this works. I'm going to go back to the question with square root. Okay. And these help pages always follow, and this is all part of the way that RStudio R is built. Right? All these have to follow a particular set of rules, so every help page will look reasonably similar. And they describe, a title, give you a description. So what it actually should do, this is free text, depending on how well they've written this. Some functions we'll come across later on are better, worse written. The usage, so square root takes one argument, x, absolute. So on this page, we also have the help for abs function, which computes the absolute value. It tells us what this argument is, a numeric or complex vector or array. We do vectors in a sec, but we know it's a numeric. Some description of the details. So here, this can be, again, free text. They're going to describe how it works. Those interested to do with how it's actually calculating these things. It's using an internal generic primitive. That's not so useful. The last thing which is really useful on this page, if I move this, is examples. So every time there's a function we come across, there'll be a working example which needs to be evaluated. Right? It's tested when they make the package. So we know that if I copy and paste this into R, it will work and it will give me hopefully a working example of this particular. In this case, I think it's doing, to try and knock two things together, it's got an absolute of this, which is here, and then it's doing the square root of the absolute. But we have an example. We know what the arguments going into the function are, and we have a description. Keep on moving this around my page. So anytime we come across a function and we don't know how it works, we can just do question mark, name of the function, and it will pull up that help page for us. If you're working in base R, it will also pull up that inside the R console. So things like the functions we just looked at, min and square root, the arguments to be provided are obvious. Square root, we know we're just going to give it a number. It's going to give us a square root. It's pretty straightforward to do. For things like min, the actual order of the arguments didn't matter. So if I do minimum 5, 4, 6, that's 4. I'm going to do the minimum in a slightly different order, 6, 4, 5. It still gives me 4. Okay, so those are very easy functions for us to use. Functions do have, though, potentially an order to their arguments. So it can actually matter which one of these goes first. And just to give you an example of this is a function we'll use quite a lot in this class, and that is dir. Okay, so let's try and look at the arguments for this dir function. That bigger, or so I can do question mark again, like I would for everything, dir. And you can see it's pulled up the help here for what called list.files, but also our function we're interested in, this dir. And this is going to produce a character vector of the names of files or directories in the name directory. Okay. And we can see already that this is a lot more complex than our square root set of arguments. It's going to take potentially up to around 20 arguments. But if we look at this now, we can actually see that many of these arguments have what is called a default. So here it's set the path to be a dot. Okay, that just means it's looking in the current working direction. Okay. In this case, we have full names here equals false. Okay, so if we want to know a little bit more about what these arguments are, we could read through here. So the path is going to be the actual path it looks in for these files. Full name, this full names argument I just talked about. If I set that to be true, by default, it's false. Yeah, full names is false. It's just going to give us the full path to that particular. Right? So if we're looking in the downloads file, it's going to prepend downloads before the name of the file. And then again, we'll have description, and we'll have some examples which we can copy and paste and just get going. This is really just to show you an example of a slightly more complex function. But as we saw in there were a lot of functions which we did, a lot of arguments which we could potentially set. So what we want to do in order to set these arguments is we'll actually give it or provide to it the name of the argument we want to set. So in this case, full names, I want to change that from false to be true. So here I can just do full names equals true. And I don't need to worry about any of the other arguments which were in that description. Okay. Alternatively, I could actually write out, without naming any of the arguments, I could write out all the arguments. So I want whatever the first argument to be passed in to be a dot, I want the second to be null, I want the third to be false, I want it to be true. But all that to really say is that all you need to do is change the argument you're interested in. To do that, just provide the name, set what you want to change it to. Okay, so we're going to come and use these functions, and we're going to set arguments a lot as we go. So don't worry, we're just going to reiterate and do the same thing until we get this. So as with other programming languages and graphical calculators, R makes use of variables. So we can assign a value to what we call a variable. So a variable really just stores a value as a letter or a word. So we can actually assign any kind of phrase or any word here. The one rule R has about variables, which I don't mention, is that it doesn't like variables to start with a number. So I can set X to be 10. And now if I type in X, X will hold that value of 10. Okay. And I can also make this obviously longer. It's on a load. Okay. But I don't think R is going to let us do anything like this. It just doesn't like us to start with a. Right. So just in case you come across this problem, all your variables, they need to start with a letter. Starting with a number, it's going to give you an error. It doesn't really tell you what's gone wrong, but it's going to say unexpected. It's the same for column names. So they do, yeah. So we're going to, they don't have types you define. So you don't need to say up front, I'm creating a dictionary. They are, and this is why R is a little slower. It can kind of define the type as you go. So there we have a question about types. A lot of programming languages up front, you need to say, this is going to be a numeric. This is going to hold this type of information. In R, you don't need to do that. It's going to decide as you assign the actual values. I will make this a matrix. I will make this a numeric. I will make this a fact. That has advantages and disadvantages. Okay. So now we've seen we can assign a value here, just a numeric, to a variable here. I'm calling it X. And now X is going to hold the value of 10. Okay. I can also change these variables. They're not what we call immutable. Once I've created them, I can just overwrite them. So I've set X to be 10. If I assign to it again, X to be 20, now the variable will change. It's no longer 10, it's 20. Okay. I've lost that first value. Variables can be used now. This X, which we've assigned the value of 20, it is as good as if I was typing in 20. It now holds that numeric value. So in this case, if I do x plus the square root of 25, it's the same as doing 20 plus the square root. X is now effectively 20. I can also use these variables to create new vectors. Right? So I can start to string these together. So in this case, if I want to create a variable y, which contains the whatever I've assigned to x plus the square root of 25, I can just write it as if I was writing 20 plus square root of 25, and I get y, which now holds the value of 25. Yeah. Yeah, I guess. No. I mean, technically, yeah, I guess. But no. There's probably a function in R which would allow you to capture both. Okay, so far we've just assigned one value to a variable. Okay, so now we're actually going to start to describe our first type of data in R, which is the most simple type of data, which is a vector. So if anyone's done other languages or any programming might consider vector to be like an array. Really, it's an ordered collection of values. And it's important to say ordered collection. Right? What I put at the first position will stay at the first position. What I put at the fifth position in my variable will stay at that. So previously we've assigned already two variables. We created x and we created y, right? These are already vectors. Okay, these are just vectors of length 1. Very simple. Again, we can already see another function here, length. And length acts like all other functions. I provide within our parentheses the variable, the argument I want to pass to the length function. And in this case, length just gives me the total number of values in that vector. So here it's just 1. So to create longer vectors, we can just use this function. We can create multiple value vectors, so we can have more than one value in it. And we just need to use this function C, which stands for combine in R. And this combines the arguments into one vector in that order. Okay, so in this case, I'm going to do C. And this is just like every other function. I have parentheses, and then I have arguments separated by commas. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now I have a vector, our first vector, to contain more than one value. And it contains, in the order we gave it, 1, 2, 3, 4, 5, 6. We can also then do, again, the length function on this, and we'll get length, and we'll find out that we have 10 variables in it. So it has a length of 10. Writing out numbers like that isn't going to be particularly useful for you, and you will need to provide strings of numbers in R. So in this case, we can actually combine our stretches of values or create these kind of continuous stretches of values just by using this colon. So here, if I want to create values from 6 to 10, I can just do 6 colon 10, and it's going to give me back a vector of length 5 containing the values from 6 to 10. So 6, 7, 8, 9, 10. Okay, so this is a nice shorthand version for creating a string of vectors. Vector string of numbers. There are, and there's a reason why, this can be not necessarily the best way to do this. So perhaps better would be to use a couple of functions in order to create our string of numbers. So we have two functions available, which we'll use quite a lot, and that is seek and rep. So the seek function, I think, takes 3 arguments. Maybe it has more. It tells you, and the arguments are from, to, and by. So from tells us where to start. So in that case, it's going to be 1, 6 and 1, 2 would be 5. I'm going to ask it to do in increments. By equals 2. We can also use the rep function. So we use the rep function and we give it here a vector I'm creating with C of 1, 5, and 10. And I'm just asking it to repeat this vector 3 times. And we can see we have 1, 5, 10, 1, 5, 10, 1, 5, 10. So already we're getting a little bit more complex. We're passing the rep function as the first argument, another function here where I'm combining 1, 5, and 10. I'm just asking it to repeat it 3 times. Okay, so once we've created these vectors, we then want to be able to access and edit and change things with them. We don't want them to be, mutable versus immutable. We want to be able to update this. So here, first thing we're going to do is just create another string of vector. Sorry, another vector, another string of numbers, and we'll use the seek function to go from to 220 by 2. That should give us here, I think it's 10, 2, 4, 6, 8, 10, 5, 6, 20. And now if I want to get access to a particular value within that variable, I need to use a different way of brackets. And here I'm going to use square brackets. I'm going to say the position that I want to extract. Okay, so for functions, we're going to use these parentheses. When we're indexing things, we're going to use square brackets. So in this case, and then different from Python, where it's 0-based. You guys don't know Python, so we don't even need to worry about that. But if we want to extract the first value, we've said 1, let's extract the first value for us. 2, if I want to extract the 8th value, say in square brackets, Z, vector I've created, then I'll say I want the 8th value. The square brackets we can use to extract values from our variable. We can also extract multiple at the same time. So if I'm interested in the 1st and the 6th, I can actually pass in another vector to say which values I want to extract. So in this case, I'm passing in a vector of 1 and 6 to my longer vector 7, this one here. And it's going to extract the 1st, which will be 2, 3, 4, 5, 6, and 12, and create that. So I can extract multiple values from my variable at the same time. I can also extract all the variables apart from a particular position. So in this case, I can do -5, and then it's going to extract all the values from Z apart from the 5th. So 2, 4, 6, 8. I should have had a 10 there, but because I've taken out the 5th variable, 5th position, I no longer do, and it's 12, 14, 16. We can also use these indices to actually modify in place. So these vectors, as I said before, we can change. So if you look at the original vector Z, you can see it goes up by 2 from 2 to 20. But if I now want to change the 5th position in my vector, I need to do 2 things. I need to first square brackets, get the 5th position from my vector, which would be 10. Then I'm going to assign to that 5th position a new value, 1000. And now if I type that vector name in and press enter, it's just going to evaluate it again, but we can see that place I've updated this value. Usefully, we can now start to mix and match. So we could use another vector, an assigned vector, to actually index our other vector. So in this case, I've got a vector y, which is 6, 7, 8, 9, 10. And I can use this to replace from my vector z, which now looks like this, 2, 4, 6, 8, 10, 1000, 12, 14, 16, 20. I can use this y to say I want to replace the 6th, 7th, 8th, 9th, 10th position from my vector z, and I want to replace that now with 0. So it's going to go in 1, 2, 3, 4, 5. I've already replaced by 1000, 6, 7, 8, 9, 10. All of those now replaced with 0. Just to hammer it home. square brackets for indexing, parentheses for functions. So just as we saw earlier on that we can use these one length variables for arithmetic operations. So I had x and I did a square root of it, or I can do x and plus a number to it. I can actually do arithmetic operations on a whole vector at one time. So here, if I have a vector of numbers, just 1 to 10, I might want to times every value in that vector by 2. To do that, I can just do x times 2. And now what it does is it takes every value within x, and it's going to times it by 2. So 1 becomes 2, 2 becomes 4, all the way up until 10 becomes 20. Okay, so now I've got a new value for y, 2, 4, 6, 8, 10, 12, 14, 16, 20. Just because I can do this arithmetic operation in one line times every value in x by 2. I can also then start to add multiple vectors together. So we can see actually here that x and y are the same length, both length 10. And here I can just add the x plus y. And what it does is it adds every element pairwise. So in this case, 1 plus 2 is 3, 2 plus 4 is 6, and so on as it adds pairwise every element. So I haven't assigned this to anything, but x plus y, this is the result evaluated here. 10 plus 20 is 30, 9 plus 18 is 27. So what happens then when these aren't the same length, right? Because x and y are the same length when I added them together here. It makes sense what's going to happen. Well, it's a little different when we have unequal lengths. In this case, if I try and add to my vector 1 to 10 here, and I try and add a vector which is just too long, it's going to do something which I guess it feels is intuitive. It's going to recycle the shorter vector. In that case, it's going to be this one, and it's going to do 1 plus 1 is 2, 2 plus 2 is 4, 3 plus 1, 4 plus 2, 5 plus 1, 6 plus 2. So it's going to add this kind of iteratively. That works well when the shorter vector can be recycled kind of into this. So this is only 2, this is 10. That means I'm going to get 5 times. But if I try and add to this vector something which is 3, that's not going to fit into our longer vector. It's going to give us a warning. Longer object length is not a multiple of shorter object. Right, and you can see what's actually happening here. So it's doing this, adding together until it gets to this one. And then it's going to try and add this vector, but it's only going to use the first element, and the rest is cut off. Something worth noting at this point here is what a warning means in R. So you're going to see a lot of warnings as you do your data analysis. Pay attention to warnings. They're going to pop up so often in your analysis, and a lot of people, when they come to me, say, I don't know what's wrong, and I sit at their computer and the warning is telling them exactly what's wrong. It isn't a dig at anyone. Please feel free to ask questions. I would rather solve it. But warnings are incredibly important. They really can. And warnings are different from errors. Okay? Errors said it didn't work. Warnings worked, but they're telling you maybe it's not what you expect. There is a danger in that if something is warning you, but it's still succeeded and you still got a result, pay attention because you might have a different result than you expect. So, this isn't just you, me too. I move forward and I realize this warning was telling me something dramatic that's affecting my results. So warnings are going to allow you to get the result, but they're going to tell you some information about what happened and potentially flag something you want to pay attention to. So I'm going to try and go to 2 just after 2, and then we'll have our first break. How far off that? So far, I've just been creating numeric vectors. Right? So things which contain numbers, and then we can do our arithmetic operations. Well, this C function actually allows you to combine pretty much anything together. In this case, we're going to combine not numbers, but now strings. So these are buildings in my old place. So in this case, I'm going to have a vector of length 3. And we're going to have 810 Commonwealth Worcester. And just like a normal vector, I can then index it and extract values. So if I want the second value of my index, I just do 2 square brackets, so y square brackets 2, and it pulls out the second value of my now string vector. We can also do something which is going to be useful later on for what is more complex indexing. So we can actually use character vectors like this to assign names to other vectors. So if I create a vector of 1 to 3, not sure why I've got C. Okay, so I have a vector 1 to 3. I can then assign to this vector of length 3 my names I've just created here by using the names function. Names, I give it the vector I want to assign names to. I give it the vector where I have the names from. Now, if I print that vector, I still have the values 1, 2, 3, but I additionally have a name associated to every value. So the use of that really is that now I can actually use those names to retrieve the values I actually want. Right? I don't need to remember, was it the first index, the second index? I can just say, okay, I want to extract 810 and Wolfson. I can provide, just as we were indexing earlier on, provide now these names to my name vector within square brackets. And it pulls out just the values which had those 2 names. If I change the order and I go with Wolfson 810 first, it would also come out in that order. With Wolfson first. If, though, I try and pull out a value and I don't have that in my vector, so in this case, I know I have 810 Commonwealth and Wolfson. If I try and pull out something called Strand, it's going to give me back something called NA. Right, and NA is a special value in R, actually a special value in pretty much all programming languages, which basically means not available. Right? So if I'm trying to pull out the index from my vector name strand, it doesn't exist. So it returns me back the special value not available. So R, like many languages, has a value to deal with strange situations, like trying to pull out something which isn't available, or I can also have situations where I do a calculation and it just can't be performed. I'm trying to times a word by 2. It's going to say, what are you trying to do? And it will give me back an NaN value. So NA means not available. NaN means not a number. So what you'll try to do, I couldn't give you a number. NAs are going to pop up a lot in our analysis. They're going to pop up in our differential results. It's kind of natural, and we need ways of handling them. So R has particular ways of handling these NA values, and I'm going to show you that when we start to deal with that later on. We're definitely going to see that in our differential expression results. A really useful function when you're dealing with strings, string vectors like this. So here we have gene 1, gene 2, gene 3, gene 4, gene 5, and then gene 1 again and gene 3. Is this function unique? So unique, if we pass it a vector of strings, it will give us just unique values within that string. So if I want to know all the genes in my table, in my vector, I don't want to have to go through and see that I have multiple gene 1, gene 3. I can do unique on my gene vector, and it gives me just the unique values. So we've had numeric vectors, we've had string vectors. Third class of vectors, which is very useful, is Boolean vectors, so logical vectors. These are simply true, false. So in R, we have special values reserved for true or false. So I don't think you can call a variable true. I think it will tell me off if I try that. I haven't tried that for a while. I get a feeling R might actually let me do this. Yeah, so it doesn't like me trying to assign something to true. Right, and that's because true and false are reserved words. Because we want to use them in things like logical vectors. We want to use these in decisions, true or false. If this is true, do that. If this is false, do that. So we can use logical vectors first off here as a way of indexing to specify the positions in a vector we want it. Okay. So true values will be returned, and false values would. So here we're going to have a vector. Now I'm going to create 1 to 10. And I'm going to use this Z vector of trues or falses to try and index this. Okay. So here we have true for the first value, false, true, falses, alternating true and false. If I use this then to index our value X, you can see all the values where it said true are pulled out from X, and all the ones where it said false are kept. That means we get the first, we get the third value, we get the fifth value, 7th value. So we don't need to just specify positions. So I want the 5th position, I want the 6th position. I can actually use logical vectors as well to take out, retrieve values from my vector or to assign values. So a common task in R, and something we'll do very early on in our analysis, is to subset one vector by the values in another. So for strings, we're going to use this in operator. And we're going to come across different flavors of this later on. We're going to have an over operator for looking at overlapping genomic ranges. But right now, we're going to just look at when strings are the same. So we'll use this in operator. And if we do A in B, it's going to create a logical vector of whether values in A match any values in the vector. So we can then use this to subset and just pull out the values which are actually in common. So let's step through this. So I'm going to create, I think I'm calling these lists. So gene list, we have gene 1, 2, 3, 4, 5, 1, and 3. If I have my second gene list, gene 5 and gene 3. If I then want to kind of look to see which values in gene list actually occurred in second gene list, I can do this gene list in second gene list. And if we look at the logical vector, you can see it's evaluated this for every value in our gene list. So gene 1 wasn't in second gene list, so it's false. Gene 2 is false. Gene 3 does occur in the second gene list, so that's true. And gene 4 is false. Gene 5 is true. And then gene 1 is false, but gene 3 occurs again here. So that's true. And I can use this logical index now to subset my gene list just for those which were actually in common. It's going to pull out just the values where it was true. Now we can gene 3, gene 5. So it's very powerful, this in operator, but it's not going to give us numbers back. It's going to give us the positions within the first one, which were also somewhere in our second. Vectors then can be evaluated to produce these logical vectors. Right? So this is very useful when we're wanting to use logicals to index. Hopefully we can already see that this would be useful. So to create logical vectors, we need to know like the logical rules in R. So to say or to compare two things, we don't just use one equal, we use two equals. So if we want to compare X equals Y with X equal Y. We want to know if something's greater than or less than, we use greater, less than, greater or equal signs. Okay. So in this case, we're going to do create a vector of x 1 to 10. And I'm just going to evaluate x is greater than 5. And this should then return a logical. And if we look, we get a logical back, false, 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 false. The sixth value is greater than 5, it's 1 to 10, 7, 8. So now we have this logical vector. We could use that to subset our values of x, where x is greater than 5. So we have our square brackets, we can evaluate this, and it comes out the value 6, 7, 8, 9, 10, because they evaluate it as true. Okay. These logical vectors can also be built up to be a little bit more complex. And we can combine these with things like and, which is the at symbol here, or, which is the pipe symbol. And we can reverse the logical operation so that true is false and false is true by using this explanation. So in this case, we just did x is greater than 5, right? Okay. So in this case, we're going to do another vector, x is 1 to 10. We'll say we want the values to be true when x is greater than 4. But I'm going to reverse it. I'm putting the reverse Uno card there. And then it's going to be true, 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 true. And then all the values where it was actually greater than 4. Now, if I want to combine that into something more complex, I can take my two logicals here and I want to say just bring me the values where x is greater than 4 and x is less than 7. Okay. So that would be the first, second, third, fourth. This is greater, that is greater, but then this value now isn't less than 7. False, false. If I do an or, give me the values x is greater than 4 or x is less than 7, clearly they're all going to be true. They're going to be one or the other. So then we can use these just as we did for standard kind of logicals earlier on. We can combine these and I can say x brackets. So you can create a logical vector inside the square bracket. X is greater than 4 and x is less than 7. We know that that was just the 5th and 6th index. If I look, 6, pull out those two for us there. And if I want to then also do x is greater than 4 and x is not less than 7, just do our exclamation mark there. So I think that's probably a good time to take a little break. We have an exercise on vectors here. Yeah, so these should be reasonably straightforward to follow. If you already know vectors, feel free to skip. If you want to kind of skip to the answers, every section we have, we'll also have a version of the exercises with the answers as well. Okay, so don't ever get to the point where you're stuck. Always look at the answers when you can, once you've given it a go. And we can pick this up. So what we'll typically do, we'll do this one today. We'll have a break now until around 3. I will come and run through the solutions with you very quickly. And then we'll pick up the next session. And then around about, we start at 3, 4. And then I'll run through the exercises just before 5. I don't mind if you need to go and step out. It's really up to you about the exercises and the answers. Everything will be recorded, so you'll be able to follow through, and I will record the solutions as well as part of this class. Okay, so on Friday, what we're going to do is something slightly different. I will do 2 sessions back to back, and then we can wait until the end of the day to go through the solution. So whatever you guys prefer, we'll probably do that vote on Monday, and we can continue the class like that. I'm going to remember to pause my session so we don't record 50 minutes of us just doing nothing. So we can use this matrix function to fill our table with vector, data coming in. We just need to specify the number of rows, the number of columns, and it's going to fill it in a column-wise manner. So by default, that's what it's going to do. You just saw that here. It's give it data, rows, columns, put it up in a column-based manner. You can change that behavior. You may well want to. And you can actually do that just by adding one additional argument here after the encode. You do by row equals true. And it does exactly what it says in the tin, rather than going by column now. It's going to fill out our matrix with these dimensions going across the rows. Now it's 1, 2, 3, 4, 5. If we want to find the dimensions of our matrix, we can use these three functions. So previously we've used length to get the total length of our vector. In a matrix, obviously we have two dimensions rather than one. So we can use the dim function, again, just passing in our matrix to the function. Our parentheses, this is our argument. And it's going to tell us we have 5 rows and 2 columns. Rows and columns. The way it works now, we've already discussed rows first. We want to get just the number of rows, like the n row. The number of rows. Given parentheses, given our matrix, we're going to get 5. We're going to get columns and columns. Yeah, 2. So it should be the same argument as we're setting here, n row and col. We can use them as functions to get the number of rows, the number of columns, or the dimensions of our matrix in one vector. These are all vectors being passed back. This is a vector of length 1. This is a vector of length 1. This is a vector of length 2, with the first element being the rows, and then the second element being the number of columns. So just as we could combine vectors together using the C function, we have the C bind function, and we have this bind family of functions, which allow us to attach vectors or matrices together. So to do this here, I've just created a set of vectors. So we have 1 to 5, 11 to 15, 21 to 22. So that's going to be 5 long. This will be 5 long, 2 long. If I want to create a matrix from these 2 vectors, we can just do C bind X and Y. It's going to take these 2 vectors and it's going to create a matrix for us out of them. Okay. It's also going to do something kind of nice. It's going to add in the column names based on the vectors we created. So I've got a vector called X and a vector called Y. When I bind these together, it's then created a matrix for me of the actual data within X and Y. But it's also giving the column names X and Y. Kind of smart. If I want to do, so C bind is column bind, right? If I want to bind rows, I can use a different function. It's the bind family of functions. I can do R bind, row bind, give it my matrix I just created, give it my vector. Now I get a matrix again, still got my column names, I've got my bind column as well. Now I've got my additional row bound onto the bottom of my matrix. See, I also have a row name for that bottom row. It's actually captured the name there, but then it's giving me that. Of course, like we had with arithmetic operations, we'll get times where these things just can't fit together evenly or nicely. So in this case, when I'm trying to create, I'm using cbind or matrix from incompatible vectors, it's going to recycle the vector like it did for our matrices. What's nice is it's going to give us this warning, which we pay attention to. Most of the time, you wouldn't expect the way you're doing this, you would expect your matrices to kind of line up. See this is perhaps telling you that you're giving it something, data which really didn't fit your matrix. So in this case, I'm going to try and make a matrix which has 2 columns and 3 rows. So I'm going to have 6 potential places to fill. But I'm only going to give it 5 values, 1 to 5. You can see what it does. It's going to work just as usual. 5 column, 1, 2, 3, 4, 5. It's run out of anything in that vector now. There's nothing more to put there. But it still wants to create a matrix fitting these values. So it's going to recycle of 1 there. That's not ideal. You'll get a warning if that happens. This is what it's doing. Similarly, if you do R-bind now, and I try and attach a row to my matrix which doesn't fit. So here I'm going to try and put to this matrix we just created here. And we can see we've only got 2 columns. But I'm going to try and add a row bind to my matrix, 5 values. It's going to give me a different warning in our bind. Number of columns of result is not a multiple of vector 2. You can see what it does. It's actually clipped the longer vector here. And it's giving me just 1 and 2. And it hasn't expanded the matrix. Just added the first 2 values of this. So it's going to be able to deal with these situations where you accidentally C-bind 2 values which perhaps shouldn't go together, make a matrix, and you have too little or too many values. It's going to tell you and warn you, but it's still going to make the matrix. Okay. As we've seen with vectors, matrices can be named. I showed you that kind of was being done automatically when we were building them just now. If we want to, then we can actually name these matrices ourselves. So in this case, I'm going to create a matrix 1 to 10, 5 columns, 2 rows. I have 5 columns, 2 rows. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's going to fill 5 columns. I'm then going to assign some column names to this. And to do that, I'm actually going to introduce us to a new function called paste. And paste just creates a vector for us. And maybe I can just copy this and have a look in R. Sorry, my computer's so slow today. Good. So here I'm going to paste together a vector called column to a vector 1 to 5. And I'm telling it one argument here, sep equals colon equals underscore. And if you look at that, it's going to produce, it's going to paste 2 column values 1 to 5. And it's going to separate this paste by an underscore. So I have column 1, underscore between it, column 2, column 3, column 4, column 5. If I wanted to, I could change my separator. Or I can change my length values here. Okay. So I'm going to use that then to assign here row names and column names to my matrix. And now I have my named matrix with column names across the top. We can then not just assign these with column names and row names, we can actually retrieve these names as well. So if I want to get all the column names for my matrix, do col names named matrix, and it's going to list all the column names for me. Do row names named matrix, pull out all the row names. So it's pulling out these names at the top here for col names, and then these names for. So these functions, col names and row names, can be used both to assign values to a matrix, but also just pull out the values from that matrix. Oh, am I making a copy? There are no like copies It's not soft copying or anything. You are altering just that matrix. So you're altering the matrix in place. So that's a concept we don't even need. I think we're going towards the concept of like copies in Python. We don't have that in R, so we don't need to worry about that. So there's a concept in Python that you make a copy of an object and you edit it. It's reflected in the original object. We don't have that in R. We don't need to worry about it. I like these questions because it keeps on making R seem simpler. There's things we need to worry about. But that simplicity which comes in R, it comes at a cost that R is doing a little bit of work for us. So if you want to then replace parts or edit parts of our, or pull out parts of our matrix, we can still use all these tricks we learned with indexing, square brackets, and now we just need to take into account 2 dimensions. So previously we just had 1 dimension. We could just do our square brackets, and now on the 5th position, I can put 5 in my square brackets. Now we have to do 2. And just as we set the rows and the columns, rows come first, columns come second when we're doing it. So if I want to pull out a particular row, I would do the name of my matrix, square brackets, and I would put the row of interest first. We do a comma, and then if I wanted to pull out a particular row in a particular column, so a cell, column, and a comma, and I would list the column. So it's the same as with vectors, but now we have to think of 2 dimensions. Okay, so here's our matrix, our narrow matrix from earlier on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. By default, working down the columns. If I want to get first column, second row, I do second row, that goes first, so it's 2. And then first column, that goes in the second bit. That's going to pull out this value. 2, 1, second row, first column, pull out. We can, though, extract whole rows or columns at a time. So here I'm just extracting 1 value, second, first column. If I want to pull out the whole second column, I can just leave the row index part of the index, so row part of the index empty. So here I do square brackets. I don't put anything into the row. I do comma, and then the column I'm interested in, square brackets. And if I pull out the column as a vector. Okay. So 6, 7, 8, 9, 10, that's our second column. If I do comma 2, it's going to pull out that as my vector. If I want to get out the third row, it's the same but in reverse. Now I'm going to put a value in for the before the comma to indicate I want the third row. But I leave blank this part where I would normally say what column. So it's going to pull out all the values for that particular row. And then I can also get a little bit more complex, and I can actually pull out multiple indexes. So this is just like we were doing with vectors, and I can pull out the 2nd and the 5th index position in my vector. Here I want to pull out the 2nd and 3rd row. So I can pass another vector to my square brackets. I'm going to go before the comma to make sure I'm pulling out rows. So I'm going to pull out the 2nd and 3rd row. Now it's going to return another vector, but it's going to return a matrix to me. Okay, so it knows I'm pulling out multiple values. It doesn't want to return a vector. It's going to return a matrix. So I should be pulling out the 2nd and the 3rd row in their entirety. As with vectors, I can also take advantage of column names, row names. So I can use these names I've allocated to a vector to pull out a particular index. This is even more, or makes even more sense with things like tables. Right, so if I have columns and maybe I want to pull out just the first column from my matrix, once I've named them, once I've made them like this, right, I can then start to use those column indexes to pull out results. So here I'm going to pull out the first column. It's from a narrow matrix, so there's 2 columns there. And it pulls out the vector containing the values of the first column. Notice it still gives me the row names, but now as standard names to my vector. Same with the rows. If I want to get the first row, use the name for the first row names. Here I just say row 1. In reverse, it's also giving me a vector, but now it's giving me a column name across the top. If I want to go like bang into a cell, I can tell it the row and the column, and I'll extract that value from row 1 here and column 1. Okay. As with vectors, matrices can be subset by logical vectors. Okay. So if I want to pull out the first here column, I can do that for my narrow matrix, and I'll get the values 1, 2, 5. Then I can also use this to extract a logical vector by just taking that column, here square brackets 1, so the first column, saying which are less than 5. And it's telling me that they're all less than 5 apart from this last row. So right, once this is extracted, it's being treated just like a normal vector. And then I can turn it into a logical vector by evaluating it what was less than 5. And then I can use that now with my slightly more complex indexing. So here I'm going to say, in the first column, which values are less than 5. And then I'm going to put that in my row part of the index before the comma. So it's going to only bring me the rows where this evaluated. So it's just going to be the first 4 rows. Row 5 had a 5. And so this row, this first column, this value wasn't less. We can also do arithmetic operations on matrices. I'm not going to step into matrix operations and maths class, but we can do some very simple things. If I want, I can just take my matrix. I could add a whole number to the whole matrix. I could add +1. And it would add 1 value to everything in the matrix. I can also just extract one particular value, add 2 to it. So here I'm going to extract first column, first row, first column, +2, 3, extract 1 here, 2 to it, or I can extract the first row entirely, row because I'm before the comma, and that would be 1, 6, +2 to that, 3, 8. Or I can apply my arithmetic function here, mean average to the whole matrix, give me the mean of the whole matrix. I don't need to turn it to a vector. I don't need to subtract anything or out index anything. It will just take the whole matrix and it will work through and give me the mean. As with vectors, we can also replace elements within our matrix. So if we want to, I can replace just this value with our dual indexing 1, 1. This first value here, I'm going to replace that with 10. And maybe I want to replace the whole column. So here I'm going to just do nothing for the row, just a value for the column. I'm going to assign that to be 1. So it should be replacing this value 1, 1, 10. And then this second column with 1. Once I've done that, you can see the matrix has been updated. So here comes the rub. Matrices can only be one data type. And that's going to sting you a little bit when you're reading in files. If anywhere in that file you have a string, it's going to turn your whole matrix to a character vector. So in this case, I do, say, arithmetic operations on the second column. And if I times that by 2, I just turn the second column into 1, right? Yeah. I can do that times by 2, and I can get the result back from it. But now, if I replace this first value, so if you look at this, you can see nothing is quoted, right? There's nothing strange about here, no quotes. As soon as I assign any value within this matrix, string, whole matrix. Now we have not a number. See, that's quoted, but everything else is quoted, not just the column, not just the row, everything in that matrix. I'm not sure what I'm going to complain about in the next. Okay. So now when I try and do an arithmetic operation on that second column, it's going to give me an error, not a warning. So this isn't going to complete. Non-numeric argument binary operation. So it didn't like that, even though it liked it, this slide here, because this quote one, let's turn it into a string and it's not going to automatically turn it back. So this type of situation is going to arise a lot. Often we want to mix numerics with a column of strings. So in this case, what often happens is someone has tuning here in your first column. Like they're not using the row name here. You do something like that, and means the rest of the matrix just can't be used as an arithmetic operations. But don't worry, we have a solution, and the solution is data. So we're not going to make this exercise just yet. We're going to skip forward a bit. I'm going to try and do factors. I'm just going to work up until 3 o'clock. But we will come back to this exercise. So factors are actually a component of the more complex matrix we're going to come up across in a bit called a data frame. But a factor is really just a special version of a vector. It's used to store categorical data. And so everything which can be grouped into categories, most often we will want to be a factor. And the reason we want to do that is because R has, once you turn something into a factor, it has ways to handle that type of data differently to a standard vector. So to create a factor is really simple. You just use this factor function. We need to pass to it a standard vector, and then it's going to create a factor. So let's have a look. We take here male, female, 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 and we do factor for this, and we just type that into R to see what it looks like. You can see it starts to look a little bit different than our normal vector in that it still has the values male, female, 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 but it has this additional component to it called levels. Right, and that's all the different categories which are in your data. So in here we only have 2 values, male or female. Let's just put levels female. Notice the order as well. So when you do a factor, you get the levels, and it's put in implicit order. If I want to see the actual levels directly inside my factor, I can use the levels function on this factor I've just created. And it pulls out a character vector just with these values, the actual values. This is my factor. It has levels attached to it. And I can do levels on that, and it's going to pull out female. So I think a nice use of why this is the most basic example, but why factors are already a little bit useful is something like the summary function. So we have functions in R, like summary, mean, min, whatever. And these functions are clever, especially, and this actually comes maybe to your question earlier on. If that summary can look at your data, it will know what type of object. So if it's a vector, a standard vector, when you pass summary a standard vector, and I think we just created this a few slides ago. Here's the vector example, male, female, female. It's going to give me some results back, and it's going to tell me the length of the vector is 4, class is character code. We don't care about this. But if I give summary on a factor containing exactly the same information, it actually gives me something a little more useful, I would say. It tells me there are 3 females, 1 male. So it's done some type of statistics on that vector straight away for us. So I said about the order. And do people have experience in R again here? Has anyone got experience in ggplot? This is what we're going to use for some of our plotting later on. And a common pain about ggplot is it makes use of these levels in the ordering of the legend, right? So if you want to get your legend in the right order, you need to get your levels. When we get onto DC2, and some of our differential expression analysis will do, Seurat as well, it takes into account these levels. What is your baseline? So often your levels, you want control to be the first. What's actually happened when we made levels earlier on is it's just done it alphabetically. Female first. Yeah. We can control that when we create the actual factor by explicitly setting the levels that we need. So in this case, I want to put male first, for whatever reason, female second. So when I create the factor, I'm not just giving it the vector, I'm also giving it another argument, the levels, and I'm going to tell it what levels I want to include in this. Male, female, and now when we get the print, even when I do the summary, the male comes first, the female comes second. When I do things like ggplot, it's going to know that order. When I do dseq, it's going to look at these levels. That's going to be important for what the baseline is. In some cases, there is no natural order to the categories, such that one category is greater than one. So we have nominal data. In this case, if I wanted to say, what was my factor 1 and factor 2? So male, female, if I want to ask, is male less than, greater than female? It's going to say warning in ops factor. There's no meaning in doing less than when I'm comparing factors with no other information. These are just categories, straight categories. It doesn't matter. But we can create factors with the idea of categories being greater than other categories. To do that, we just need to add an additional argument to our factor, that is ordered. So this may be important when we get to dseq2 and we have categories which have meaning in terms of this is the smallest. This. So here again, I'm going to pass in my vector small, big, big, small. I'm going to tell it it's ordered, it's true. And then when I set the levels need to be ascending order. So here, small and big, and small is less than big. And when I look at the actual factor, you can see it still looks the same here, it still has levels. But previously, it just listed the levels, I think. Male, female, side by side. Now it's going to say small, less than big. If I had more, it would say less than, humongous, less than, gigantic, or whatever. So the levels now have actual order. And if I say here, is the first small less than the second big, it knows if you look at the levels and say, yes, that's true. Yeah. So we can have, I think it's ordinal data. Yeah. I think something which is a big pain in factors, big pain in data frames which are built from factors, is this concept of replacement. So unlike vectors, replacing elements within a factor isn't as easy. And already we can see why. It's because we've told it the levels. So we've told it what to actually expect in this factor. We've told it at this point, there's just two, small and big. Right? When I was doing male and female, I was saying just two for male and female. Right? So actually replacing elements within a factor really isn't so easy. So in this case, I'm going to create a factor. It's going to be small, big, big, small. If I want to replace just the first element, I can replace it with a value which was at my levels. So I'm going to say the first element's now big. If I look, yeah, big, 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 small. My levels remain very same. But I didn't set the order. Levels. If though I want to add to my factor a value which isn't in my levels, it's going to go warning, factor, value huge, invalid factor level, generate. Then it's going to then put at that position this NA value, not applicable, not available. Okay, that's because in the factor we're trying to introduce something called huge, which wasn't in the levels. It's going to tell us all. We have to go fix this problem by adding new levels to our factor. So if we want to do that and we want to update our factor, the first thing I need to do is what's called re-level our factor. I'm going to use the levels argument on my factor, but I'm going to assign new levels to it. I'm going to give it big, small, huge. Could have chosen a more sensible order. But now that I've added that here, I can assign to this value huge. It's not going to give me an NA. It's just a set the levels so that I can include that because it knows, it's aware of this category. If I try and add a value to a factor and it's not in its levels, its categories, known categories, it won't work. So we'll see how far we can get in data frames. We'll see how far we can get in data frames next. So data frames, I really think, are a fantastic thing in R. The thing which I think Python has perhaps tried to copy a little bit with the pandas package. These are slightly more complex objects, but they are super useful because whereas when we looked at matrices, we could only have one data type in this kind of table. In data frames, we can have multiple data types. And in fact, it's the column that's needs to be one data. So in this example here, we have our row names. Then I have perhaps here my actual gene names in column 1. I have a numeric value, column 2. And then I have here something to do perhaps with the gene. Another, this could be a factor, for instance, so a multiple transcription. And so I can have different types of data within a data frame based on the columns. So in R, to make use of a data frame, you need to use the function which is there to create data frames, and that is data.frame. I'll show you later on there are ways of turning matrices into data frames. In this case, I'm going to create this from 3 different vectors. So first, I'm going to have a vector which is just my patient names, patient 1 to 4. I'm going to have a patient type. But it's going to be male or female, so we'll have categories. So I will make that a factor. Here it's just repeating male, female twice. And then I'm going to have survival time, which isn't a character vector, but a numeric vector, 130, 20, 20, sorry, 220, so 130. Once I have all these vectors, I can create my data frame from this. All I need to do is data.frame. I can list now within the same thing as always. We have our commas separating out our arguments. And every argument here, I'm doing, say, name was patient name. That means I want a column called name. And I want to put the patient name data in that column. Or type column, a name called type. I want to put patient type there. And then I want a column called survival type. Time. And I have survival time. So naming the columns I want within this data frame argument. Then I'm saying, assigning to those names the actual values I want to get. And then we have our data frame. But I think what's already apparent is it hasn't quoted survival. Quotes, these are still numeric. These are factors. Mix all these different data types into this one object, a data frame. I think, already this is just going to be super useful because we can store metadata alongside numerical data, alongside factors. Great. So data frames can largely be used or indexed just as matrices. So if this is our data frame, now I want to quickly pull out just the rows where we have patients with survival time above 10. I can do data frame comma, I pull out the survival time column, check which values are above 10. So that's going to give me a logical here, just saying which values here are above 10. And I'm going to use this whole thing here as my index for rows. I'm doing a comma, but nothing in the column bit. So all this will be my logical index. So it's going to pull out false, true, false, true. And then it will subset my data frame now. I couldn't do this with a matrix. It would be, this would have been turned into a string. Unlike matrices, you can actually do some nice, again, data frames, they cost a little bit more computation. But you can do some nice kind of indexing tricks. So we don't need to actually do this square brackets thing if we want to pull out a particular column. We can actually do this dollar symbol. So we get the name of our data frame, we do dollar, and I put the name of the column I want to extract here, survival time, and it will extract that column. So this is the same as indexing with square brackets, except I can just use dollar and the name of the actual column I want to pull out. So then I can use that, as I said, use that then just like I did with square brackets. So in this case, I can do what I did in the previous slide, where I said df example square brackets, survival time is greater than 10. Now I'm going to do dollar, survival time is less than 10. That actually looks a little simpler for me. Just take those. It looks a little simpler than maybe the previous slide. A really nice feature about data frames, though, is that R is actually going to do some autocomplete for you. Right, so if you have these really long column names, as long as the column name is unique enough, if you do dollar and serve, there is no other column name we have which is close to that. If I had, I don't know, swim time or something, I would need more than an S. I would need to put the U there. But R is clever enough that it's going to go, okay, you want the survival column, it's going to pull out the values. That doesn't work with standard. It only works with data. If you try and do like a semi-complete value here using the column names, it's just not going to work. Really usefully, we can actually also use this dollar operator to actually create new columns on the fly and just add them to our data frame. So we don't need to necessarily C-bind things on. If I wanted a new column called new column, I can just do the name of my data frame, dollar, the name of the column I want, and I'm going to call it new column. And I can just assign values into that. Again, it's like matrices. If I give too many values, it will recycle or flip. But here I'm going to say repeat new data, so string. The number of times I want to repeat it is the number of rows in my data frame. And then I'm going to get 4. So I've got a new column containing the strings. So we can kind of on the fly add additional columns to our data frame here. So let's see how much we have left in this particular session. So we can also do replacement, as we've done for the less complex data types. So in here, if your survival time is less than 10, so I'm going to find the rows, so I'm going to find the column values for survival time, which are less than 10. I'm going to use that to subset my rows and look in the survival time column. And any time that it was less than 10 now, I'm going to assign a 0. And I can update this data frame just as I would a matrix, just as I would a vector. 0, 0. And previously, I think it was 1 and 2 or something. Right, so just the positions in there. It was less than in that particular column. 10 replace in that column. It's it. Gets a little bit more complex though when we start to look at columns in my data frame which are factors. So we know that this column here is a factor. Now, if I try and assign to their other, I have the same problem I had with the factor. What we've already seen before, that a data frame is constructed of multiple kind of linear data types. So this is a character, this is a factor, numeric. That's a vector. But we can't replace a factor with a new value which wasn't in that factor levels. So I'm trying to replace it with other, and it gave me exactly the same warning as I saw previously. The solution is simple. I need to update the levels in that particular column, just as I did previously. So I just rebuilt my data frame again. And I'm going to do the levels of that particular column, the type column. I'm going to set them to be the current levels plus combined with something called color. Now, when I try and assign to that first row type column here, other, I don't get a warning. So data frames have these advantages, but they also come with a cost. You need to worry about things like levels and replacement inside them. Oh, I was hoping for this slide actually. So the real problem with this was that when you read in any type of table in R, up until I think R4, when it read in the table and it tried to make you a data frame, it was converting any strings to factors. So if I read in this table here from a file, it would make patience factors. It would make type factors. Anything which didn't look numeric, it would make a factor, which is a pain because then you need to worry about this levels thing. Okay, this thing we were just worrying about here. Actually, that updated since we've been doing this class. I guess they reckon that wasn't a sensible default. So when you create a data frame now, this used to be default true. You have this additional parameter strings as factors. I think by default that's now false. But if you set that to true, sorry, was that a sneeze or a question? If you set that to true, now anytime we try and replace anything within columns which were strings, we're going to have this problem with factor. The reason we point this out, I don't think anyone here is going to be before R4, is there are lots of manuals still online which try and deal with this. And they're going to show you this problem. It got updated about a year ago, this issue of strings as factors. But if you want to force yourself to deal with it again, you can actually set it by default. So in this case, even the name column got turned into a factor, which makes no sense because you know, every single value would be different within it. It's no point of being categorical. So now R lets you choose by default. Lets you set this as false by default. If you look at this one here, if I just create the same data frame again, and I try and replace one of these names here with, say, patient X, two of these names, that will work fine. But if I set the strings as factors to be true, anytime it sees a column with any strings in, it's going to make it into a factor. So a really useful function in R is this function order. So for numeric or vectors, order by default returns the indices of a vector in that vector's increasing order. This can be altered by setting the decreasing. So if we set decreasing equals true, it's just going to flip the order. So in this case, we have 20, 10, 30. If I pass that to the order function, to this vector, and I say decreasing equals true, it's going to tell me the third index is the biggest, and then the first is the second biggest, and the second is the biggest. If I change this to decreasing equals false, we go the other way. So this is really useful for when we want to reorder things like tables or data frames. So once you have a vector of ordered indices, we can just see here, we can use this then to reorder this case, I'm going to give it our vector here, pass it to the order function, and it will give me back the indices of this in the order of their increasing. If I set decreasing equals true, we can move back in there, decreasing. This just means I can pass the result of this as an index for the vector I'm ordering, and it's going to give me back that index either in increasing order or here decreasing. So again, but when a vector contains NA values, these NA values, these not available values, by default will be placed at the end of the order. So in this case, if I have a vector 2, 1, NA, not available 3, and I try and order that here, decreasing equals true, you can see it's going to put the third one first, the second one there, the first one there, and then NA up there. And that's because I put NA last. If I do order and I set that NA last, it was false. It's going to put NA at the very beginning. NA can't be ordered. It's not available. So it has to put it either at the beginning or the end. This is kind of useful when you're wanting to pull out the top and the bottom of a list. If you get this wrong, you do NA last equals what false here. When you look at the top of the list, you'll find it has all the values where it's NA. So we've got an example of this coming up in the exercise, sorting with a data frame which has NAs in it. But by default, it's going to make a sensible choice. It's NA last equals true, and it's going to put any NA values at the end of the ordered list. All right, so let's use this now with a data frame. So we have our data frame here, DF example. We have a column of survival time, 1, 32, 20. So I want to reorder this going from longest survival to least survival. All I need to do then is pass in the order, give it the survival column, and here I'm doing $serve. I don't need to write out the whole name because I'm doing $. I can just list the unique part of the column name here. And I'm saying decreasing equals true, so it's going to try and order these from decreasing to highest to lowest. And I'm going to do it for the rows. Yeah, so the comma, and then nothing in the column. And now it's giving me the indexes of this in order, which means it's going to order my data frame now, 30, 22. So already I can do some slightly useful things. I can start to sort my tables by particular column in my data. We can also then supply multiple columns to organize by just providing them to the order function and then separate it like we do with all arguments by column. So here I want to order first by the type. Then I'm going to order by the survival. Then I'm going to order, that's it. Just order by type, survival, decreasing equals. So that means then it's going to look at the type. It's going to use the factor to order it. Okay, when we made this, female came first, male came second. So decreasing equals true is put male first, female second. That's just the order it was in our factor. And then it's going to order the survival time from decreasing to highest to lowest within these groups. So first it sorts them into male and female, and then within male it sorts the survival time, and then within female. We have any number of things to sort by here, to separate them. Okay, so last week. It gets a little bit more complex. I was actually thinking that when I was looking at the slides yesterday. So no, you can't just do it in one order for decreasing first. I've seen the simplest thing here is actually just to re-level the type. Yeah, no, we have. I can show you a different kind of combined order. So one thing which is super useful about data frames, and you're going to do this a lot, is joining two data frames together. So often you'll have a matrix of all your results or a table of all your results, and then you'll have a table of additional information, say on the genes. And you'll want to put this into one table so that you know your differential expression results, but you also know what the genes do or something like this. So we can merge multiple tables by using a function in R, which is going to be called merge. First thing we need to do is create two tables. So we'll create one table from our data frame, give a patient name, give a patient type, give it a survival time, name, type, survival time. And then we're going to do another one, but we're going to have a common column here. I'm going to give it the first three patient names, so 1, 2, 3, and I'll give them some types. So now I want to find a way of kind of combining these two tables by the common elements. So perhaps the easiest or most straightforward way to do this is using the merge function. So there are lots of other merging kind of tools, but merge is base R, what we can use to do this. So merge takes a few different arguments, but the first two arguments will be the first two tables you want to merge. Merge can only merge two things at a time. Can't give it 10 tables at a time. Success. So here I'm going to give it the two tables, data frame 1, data frame 2. I'm going to tell it the column I want to merge by. Here I'm telling it the position of the column, telling it what. I can also give it a quote. I'm sure if I show this. I can also put in quotes the name of the column. So actually, there's a column called name, which is common across both of them. So I could do by equals name. That would also work here. In this case, I'm going to do by equals 1. It's going to just tell me, it's going to say, use the first column of both data frames to merge. Finally, I'm going to set all as false. And that means it's only going to keep elements which are common to both data frames. So we had, I don't think I have much in. We had one column which isn't in the second data frame. So patient 4. If I merge these, then patient 4 had no information in the second data frame. So what it's done is it's just given me the common names across the two, and then it's merged them such that this part is from our first data frame, this part here, height, then from our second. I have to combine these two tables together just by using this column which we specify either by number, position, or in quotes by the actual column name. The all equals false or all equals true. We've got an exercise on this, but if I said all equals true here, it would have brought in the patient 4 information, the table it was in. So I would have got this information here, patient 4, female 20, but where it had height information, I would have had NA. So you're going to see NA by 1. So I think that's it for our sessions today. I have some exercises on data frames and matrices. If you want to run through them, I will be in class here until 5, and I will go through them around 5 o'clock. We can just go through them together. If you want to go home, this is all recorded. You can pick it up. I'll try and put it on YouTube tonight or tomorrow. Great. Thanks, guys. So there's no more teaching today, just to run through the exercises.